transformative power of ICTP. This is early 80s, and for many of our professors, ICTP was the gateway to the scientific world. I still remember the excitement when they would come back and tell us about what they were learning. So I was so thrilled and very proud when Atish was appointed the director of ICTP. And this theme of bringing science to the world, joining the world is part of his title today, to unite the world. Atish got his PhD at Princeton, and after that was a postdoc at some of the top places in our field at Rutgers and Harvard, and had a longer-term position at Caltech before coming and joining TIFR, where he was for several years until he moved to France and now Italy. He's a very well-known, famous string theorist who has made a number of landmark contributions in the field. I'll mention two. One is pertains to work he did as a graduate student, where he found a special class of string states. They're now called the Dabholkar-Harvey states in his honor and his advisor's honor. And they're a special class of states whose mass, for example, is protected as you change couplings and so on. And these are invaluable, as it turned out, as our understanding of string theory progressed. Such states, highly protected states, are invaluable to be able to probe the sort of strongly coupled, non-perturbative behavior of string theory. And really his work presaged that set of developments. One way in which those kinds of states play an important role is if we try to count the microscopic entropy of black holes from first principles. How do you account for the entropy as log of some number of states? And this is a problem which has, Atish has worked on, over the years. I think he first started in a serious way, perhaps here in TIFR, and continued that, and has had a great deal of impact in the field. It's a beautiful subject he has helped develop with some of the leading mathematicians, also connecting the work of Ramanujan, mock modular forms, and so on in number theory to the counting of black hole states. And I think perhaps we'll get a glimpse of some of that also in his talk today. I should say that he's a recipient of a number of awards, including the Bhatnagar Award, and is also a member of the Indian Academy of Science and the World Academy of Science, and so on. A great privilege to have you with us, Atish, to tell us about joining forces to unify nature and to unite the world.
Thank you. Okay, so it's really a great pleasure. It's like a bit like homecoming. I have spent here more than 10 years, and it's good to be back among friends. Sandeep and I go a long way, as you said. I think you shouldn't be mentioning such big numbers. So actually, it also happens to be the 100th anniversary of the founding director of ICTP, Abdus Salam, who made pioneering contributions to this idea of unifying nature, unification. So that's going to be my theme today. I basically have divided my talk in two parts, but actually there are four parts. I will first start with this idea of unification of nature, which many of you know, but in physics you know, but also there are people from other areas. So I want to explain why this idea of, how the idea of unification has evolved over the years, and how that remains a kind of an inspiring principle for us. Then I want to tell you about ICTP and the role it has played to unite the world by joining forces in the literal sense. And then my first part, I will do this, explaining the history. And then after the later half would be to explain the future of these ideas. What is the future of unification? What my generation, our generation is doing? And what is the future of ICTP? About how we imagine ICTP will continue to unite the world in the coming 60 years. We just celebrated our 60th anniversary. So my first talk will be about the past 60 years in both these themes, and the second half would be the future 60 years for both these themes, okay? So bear with me, and don't stop me for a question if you have. So we are going to start at the very beginning from the point of view of the ideas of unification. So all of you know electricity and magnetism, and not everyone here would know that they are actually unified in a very fundamental way. It is one of the first examples of unification. So here is electricity, we all know, and here is magnetism. They are drastically different physical phenomena. No one in their right mind would think that these two things have anything to do with each other. But they turn out to be two sides of the same coin. So it's like, this is the idea of unification, that very diverse phenomena look like diverse manifestation, but their underlying reality is the same. It's the single whole. So they are joined together. These two forces are joined together at deeper level, and that is what we mean by unification. So I started at 1610. Okay, so I have till 1710. So this one can say is the electromagnetic unification. And how does it work? So basically, you know that the electric charge creates an electric field. But if the electric charge is moving, that's like an electrical current. And you know that a current creates a magnetic field going around it. So it's natural to think that these two phenomena must be related. Once you understood that charge creates electric field and current creates magnetic field, and this was made precise. Basically, magnetism is electricity in motion, would be the slogan. And James Clerk Maxwell wrote this beautiful set of equations. Here are these equations. You can write them on a piece of paper, on 2 lines actually, where F is an entity which is like the electromagnetic field, but basically you know there is an electric field and a magnetic field. Like when you put some iron filings around a magnet, you get this in a picture of a field. There is an electric field and a magnetic field, and they are all combined into one single quantity, F, because now they are unified. And the equations look very simple. This turns out to be a second order differential equations. Okay, so it's not. And what is spectacular is that then he not only unified electricity and magnetism, but he also unified light. So they turn out to be 3 sides of the same coin. You have electricity, you have magnetism, but once you combine them into these equations, which I wrote down, they have wave-like solutions. So they have a wave-like solutions in which the magnetic field is going up and down like that, electric field is going up and down like that, and the wave is traveling. And to his surprise, without putting any information about it, that speed of that wave is actually the speed of light. So suddenly, light came as a manifestation of electricity and magnetism. So light is now unified. But not only light of every color, blue, green, red, X-rays, radio waves, everything that we really use, all communications, is all electromagnetic waves of just the different wavelengths change the character of. So this is actually a very spectacular unification, if you think about it. Extremely different phenomena, X-rays, microwaves, radio waves, light, green, red light, electricity and magnetism, is all contained in those simple equations I wrote down. 2 equations really seriously contain everything that you want to know about this phenomenon. But we know, you must have heard, that photon is the quantum of light, that sometimes this wave actually behaves like a particle. And in fact, this classical electrodynamics described by his equations is kind of an approximation which is good when the number of these particles is large. And that is known as quantum electrodynamics. And just to give you an idea, quantum electrodynamics has been so successful that you can sit in your office and calculate this number. I mean, it takes it will take you many weeks. It's a very long and difficult calculation. And there are very subtle and difficult experiments, and they seem to agree to so many significant digits. This is perhaps one of the most striking results in physics, where theory and experiment agree. But then comes Rutherford, who discovered in his famous experiment the atomic nucleus. And the atomic nucleus had new kinds of forces. It had a strong nuclear force, which seems to hold the nucleus together, and the weak nuclear force, because of which the nucleus decays. So radioactive decay was known. This is Rutherford. So he discovered, and it's a very simple experiment he did actually, gold foil, and he bombarded, and I have seen that original experiment in CERN. It's really a tiny experiment, and you've bombarded it with alpha particles. And he was shocked that once in a while that alpha particle would shoot back at him as though it had hit something very hard. And that led him to understand that actually most of the positive charge is actually concentrated in a very, very, very small part of the atom. And that's how we came up with this planetary model, that all the positive charge is in the nucleus, 1,000 times smaller than the atom, and the electron is just going around it in like a planet. And this was the big breakthrough. And this, not only was this a conceptual breakthrough, but also an experimental breakthrough, because that's basically still the method that we use. This is, as you know, in high school you learned that the nucleus is made up of protons and neutrons in turn. And now we are smashing protons into this huge accelerator in Geneva, several kilometers long. And this is an enormous detectors. There is a human being standing over there, okay? So this is what it takes to now detect this. So this Rutherford small experiment has now blown up into this big experiment. And this is still the method that physicists use. It's like you want to learn how a car works. You are sort of smashing two cars together, and you see a steering wheel comes out or a tire comes out. And then you say, okay, there is something called a steering wheel inside a car. And that's the method that Rutherford initiated, and that's what we continue to use. But now that raises a question. Okay, you have unified electricity, magnetism, light. I mean, that's a lot. What about these forces? What principles govern these forces? And again, you have to look at it historically. Now it's part of textbook. But this was an absolute mystery because they are such different forces that even one of the great pioneers in quantum electrodynamics I mentioned, Freeman Dyson, he declared in 1960, the correct theory will not be found for the next 100 years, okay? And very eminent physicist who was very eminently wrong, okay? Because literally in 15 years, the theory of these two forces was completely well understood. And that has to do with a principle, a new principle, which is called the gauge principle, okay? And I'm not going to explain it in detail, but basically this idea of SUN quantum gauge theory is some generalization of this Maxwell's equation that I wrote down, okay, roughly speaking. And the idea is kind of not, so this is what I would call unification of principle. It's not only unification of forces, but you have suddenly discovered a common principle describing very different forces. And the principle is actually sounds like a fairly obvious and almost kind of a childish generalization that, okay, we had this electromagnetic field and it was associated with one kind of charge, and the charge can take many values, +1, -1, +2, -2, 0. But there is only one kind of charge. Now, what if you have two kinds of charges, like up charge and a down charge, which each can take value +1, -1? Then it turns out the field has to be, a 2 by 2 matrix. Okay, this is called a 2 by 2 matrix. You have 4 entries, and the charges are 2 charges. Then obviously you can do 3 by 3 matrix and 3 charges, n by n matrix and n charges. Okay, it looks like a simple generalization. And just like I wrote down the equation of Maxwell on 2 lines, you can write down these equations for these fields in 2 lines. It's very easy to write down. And amazingly, I mean, this is one of the wonderful examples of human beings doing some fairly simple sounding generalization, but it actually does describe nature. And it's actually surprising, and it didn't have to be that. And basically one charge corresponds to U1, SU2, SU3. I mean, these are some technical terms, but like 1, 2, 3 correspond to having 1, 2, 3 charges. And if you have n charges, you have SUN. And this describes electrodynamics as Maxwell discovered, but this describes the weak nuclear force roughly. And this describes the strong nuclear force. So we are done. By just generalizing up to 3 by 3 matrices, you can describe basically everything from nuclear reactor, nuclear bomb, radioactivity, to X-rays. So essentially everything in this room you can describe in terms of these simple equations that you can write down. So now the question arises, can you join now the electromagnetic and weak force? Okay, all very good. So far, electricity, magnetism, light has been unified. We have found some general principle to describe all these forces. Could the weak nuclear force be joined together with the electromagnetic force? And once again, there was a very eminent scientist who, Wolfgang Pauli, he said that when actually Salam wrote to him about this idea, he said, let no man join together what God hath torn asunder. Okay, it's a joke on when people get married in a church. The priest is supposed to say, let no man tear asunder what God hath joined together. So, but it turned out that Pauli, who was one of the founders of quantum mechanics, was more witty than wise. And he again was eminently wrong. And good for Salam that he didn't listen to him. So the lesson is that don't listen to eminent scientists. And he actually succeeded in doing the electroweak unification. It had lots of very new ingredients, which you might have heard: spontaneous symmetry breaking, Higgs mechanism. Many new particles had to be necessary, which were predicted. What is called a massive vector boson, a Higgs boson. You must have all heard about the Higgs boson. And when these discoveries were made, this led to the 1979 Nobel Prize to Glashow, Salam, and Weinberg. So this is Salam in the middle. So I want to now explain to you the idea of unification by an analogy. It's like this. Imagine that there is a temple of electromagnetism where you worship the deity of electromagnetism. Okay, there is another temple of weak nuclear force where you worship another deity which is called the weak nuclear force. One day, somebody who is digging in the yard of the temple discovers that there is actually a secret passageway that takes you from one complex and to the other. And in fact, they are actually connected. They are part of the same temple complex. And that would be the electroweak unification. So this is the Meenakshipuram temple. So now we have the standard model, what is known as the standard model. But you must have seen this many times probably. But basically with just a list of a few particles, up quarks, down quarks, neutrinos, electrons, photons, gluons, vector bosons, you can describe electromagnetism weak, strong, and the Higgs boson. So basically, it's an amazing achievement for the human mind. If you think about it, our brains evolved to pick berries and throw stones, but we are doing some of these very subtle experiments and very subtle theory, and we are finding that the two things agree in great detail. So this was the first track of my talk. So I have basically told you everything that we know about particle physics up to now through many, many experiments and all the theory. Now I want to go to so this is joining. We have joined lots of forces, as I've described, for unifying nature. Now I want to tell you about joining forces to unite the world. So this is the Abdus Salam International Centre for Theoretical Physics. This is the campus of ICTP. It's in this very beautiful location on the Adriatic Sea, right next to this nature park. Actually, it's a bioreserve. It's a beautiful park. I want to tell you now what ICTP has been doing and how it has been joining forces to unite the world. So ICTP's fundamental mission is international cooperation for and through science. We are a UN organization, so we are all UN employees, founded in 1964, governed by a tripartite agreement between two UN organizations, International Atomic Energy Agency and UNESCO, together with the government of Italy, who is the host country. And Robert Oppenheimer was the first chair of our scientific council, who was tasked to see whether this idea makes sense and give some structure to ICTP's governance. And our idea is to overcome the barriers of gender, ethnicity, geography, and economics. And you can see here various people, some of them, Juan Maldacena is a very well-known colleague of ours from Argentina, and he often describes how ICTP indirectly shaped his career because his advisor undergraduate advisor went to ICTP And Salam told him, drop everything and study string theory. So he went back and started to study string theory, and that's how Juan Maldacena got interested in string theory. Here is our colleague Ashok, who got the Dirac Medal from ICTP, a very prestigious prize. So we have had now more than 200,000 scientists who have visited ICTP over the years from 188 countries. 67% are from developing countries, fully funded by ICTP. About 30% are women. We every year have 60 conferences, and it has had an enormous impact, as Sandeep also mentioned. And I have also witnessed myself, even when I was a professor at TIFR, not only student. It has helped enormously to build scientific communities around the world. And we have contributed to many breakthroughs, including to 5 Nobel Prizes. So it's an international hub for science. That's how I envision ICTP, not only for developing countries anymore. And it has this unique mission that excellence at the frontiers of science, that is, we are not some service providing institute, but global inclusion, for not only for gender and ethnicity, which is often talked about and which of course is important, but very often geography and economics, which is also sometimes a bigger determining factor, and international cooperation for and through science. And this is actually, as you can see, as the world is getting more fractured, this is also going to be an extremely important role of the mission of ICTP, and I really take it very seriously. And this is a very nice quote of Salam from his Nobel Prize, that scientific thought and its creation is the common heritage of all, his creation is repeated. Scientific thought and its creation is the common heritage of all humankind. Not only, and there are several examples of major breakthroughs coming from all over the world. And it's fundamentally important that we are not only using science as, consuming science, but we are actually creating science. And this is, of course, how TIFR was conceived. So this is ICTP at the United Nations. So in the 60th anniversary of ICTP, we were invited. I was very honored to represent ICTP in this high-level meeting in front of the member states of United Nations. Here is actually Duncan Haldane, is a Nobel laureate who came. But what we did was we invited 3 testimonials, and I just want to tell you about them. So this is Raji. He came from a small town in Ethiopia, from a modest family with 4 children. And it was evident that he was very bright. So his professors realized, and he said, I want to do physics. So they told him, if you want to do physics, go to ICTP, because his professor had been to ICTP. Then he came to ICTP to our master's program. And as it happened, he did a very nice, like an holography or something, master's summer project with me. And now he's doing his PhD at MIT. So this path would not have been available to him. This is Estelle. She's from Cameroon. She also was a PhD student at ICTP. Then she did postdocs, and now she was at Perimeter. She's working at Perimeter. But now she has gone and founded her own company. So she has become an entrepreneur. And this is Minister Rapapa. He is the Minister of Science in Lesotho. Lesotho is a small country inside South Africa. It's a landlocked country. And he was a student, and he remembers ICTP with great fondness. He came all the way for this program. And he said that it really changed my life. And it's very important that people who have studied serious science are in position of policy making in countries like Lesotho. So ICTP also organizes activities around the world to a smaller extent. I mean, our primary thing is that we have activities on our Trieste campus, but you can see it really has an impact all over the world. Now, about ICTP in India, I can say more than 12,000 scientists from India have been, actually the number is more like 14,000. This is, a slide is old. And we are now working on agreements with DST, Ministry of Earth Sciences, several institutes to increase this collaboration. Major conferences, I remember, like Strings Conference, which we organized here at TIFR, we had all these very eminent people, Witten and Gross and Hawking, but we didn't have the funding to, it was to get foreign visitors. And I remember going to ICTP and talking to the deputy director of the time. And they immediately gave us 30, 40,000, I forget the exact number, which was really crucial for Strings conference to be. So in a way, ICTP was acting as a, as I said, lighthouse. So it has really helped in internationalization of Indian science, nurturing the research environment in India. And now really is the time for equal partnerships, which I will describe later. So this is again history of ICTP, last 60 years of ICTP. So this was the second strand of my talk. Okay, now I want to go back to the first strand, which is unifying nature. Okay, now you can tell me we have unified three forces, but something very important I have left out. Gravity, right? This is the first force that was really discovered by Newton. That's how modern physics started, and I have left out gravity. So the force of gravity, of course, goes back to Newton, and it amazingly predicts planetary motion in great details. How does gravity fit into this framework of unification? That's a very natural question. Can the force of gravity be unified with other forces? And this is what is driving the research of all my colleagues in string theory and related topics about how do we unify gravity with the rest of the forces. But before we unify gravity, you need to actually unify space and time. So this was done by none other than Einstein, because he realized that time is relative. Okay, that's why the name comes, relativity. What does it mean? That Newton believed that time is absolute, which means my time and somebody who's on the train, their time is exactly identical. If I say 5 seconds have passed, this person on the train would also say 5 seconds have passed. But Einstein thought carefully about how we actually define time, taking into account the fact that speed of light actually doesn't change in any frame. This is quite a shocking and counterintuitive statement, because if you throw a cricket ball, if cricket ball is going, then at 50 kilometers, it looks like it's going at 50 kilometers. But if you get onto a motorcycle at 50 kilometers, then you're going along with the ball, and then the relative speed is 0, and you can catch the ball. So the speed of the ball depends, whether it's 50 or 0, depends on which frame of reference you're using, whether you're on a motorcycle or on a train. Somehow that is not true for light. And that very counterintuitive fact implies that time has to be relative. And so Einstein said that, okay, let's define a clock by just saying that you take two mirrors and you send a light up and comes down. And when it comes down, you say one unit of time has passed. And then there is this very nice video. Moving clocks run slower. So here is a clock, two clocks, they start together at 0, 0. One clock starts to move. And the light is going back and up and down, up and down. So when this clock shows 5, this clock will show 4. But why? It's very easy to understand. Because see here, the light in this clock has to travel much longer distance, right? It has to travel on the diagonals, whereas this is going just up and down. If he has to travel at longer distance at the same speed, since the speed of light is the same in both frames, then, I mean, this is the kind of thing I used to torture my son with when he was 12 years old, that now using Pythagoras theorem, you can actually calculate Lorentz transformation. And in fact, this amazing famous formula like E is equal to mc square follows from this very fundamental. So it's actually a power of human thought that if you think carefully about relativity of time, you are actually forced to accept that time is relative. And from that, it's one step to say E is equal to mc square. Okay, this I will not explain. But here is very geometrically clear. Just because the light is traveling longer distance, it is more time has passed for the moving clock. So this suggests a universal speed limit, because if the speed of light is the constant, if you now follow these Lorentz transformation laws, you cannot exceed the speed limit. So this universal speed limit is 1 terameters per hour, okay? I mean, 300,000 kilometers per hour, but it's roughly 1 terameter per hour. It's an enormous, I mean, even a normal rocket goes like 1 kilometer per hour. So this is enormously large speed, but that's the ultimate speed limit. You can never, no phenomena, no influence can travel faster than this. And this has two very dramatic consequences. One is gravity waves, which you must have heard about, the gravitational waves, and other is black holes. And that's what will bring it to my own work. But I want to explain to you the idea of gravity waves because that connects to unification of space, time, and gravity. Okay? Because this, so far I have told you there is a universal speed limit and gravitational force. You remember Newton's law of gravity, right? Even those who are not physicists, right? You remember that Newton's law of gravity is like between the sun and the earth is the mass of the sun times mass of the earth divided by the square of the distance between the two times some constant, right? Now, there is no time in this equation. So my question to you is that, suppose the sun disappears now, when will you come to know on earth? Non-physicists have to answer this question. Right? There is a logical inconsistency because if the sun disappears, when will we come to know about it on earth? According to Newton, instantaneously, right? Because there is no time in his equation. You put mass of the sun to be 0, then the force is 0, right? But according to Einstein, nothing can travel faster than the speed of light. So how is this two things can be consistent? And this is actually led to, this was a really bothered Einstein. But it's actually very interesting that it bothered Newton also. So Newton, being Newton, understood the weaknesses of theory very well. And he actually, there's a very nice couple of passages, and now I won't be able to recall exactly, but he said that nobody in the possession of their mental faculties can make such an absurd statement that if I wave my hand, the moon will shake, That's what his law suggested. And he understood that it's crazy. And some of the people criticized him. And he kind of made a wise tactical decision to say that, okay, nevertheless, okay, but I still write down these equations and I'm able to calculate the motion of the planets. But he understood that there was something wrong about this action at a distance. So he was really seeing 300 years ahead of time because it took 300 years before this logical inconsistency was resolved in Einstein's theory. And in Einstein's theory, where you unify now gravity and space-time. So now our unification has come very far. We have unified all these forces of electricity, magnetism, light. Now we want to unify space-time and gravity. Now, what does it mean, unify space-time and gravity? What Einstein realized is that gravity is a curvature of space-time. So imagine that you start out on the surface of the Earth at the equator, and you're just going straight ahead to the north, right? If you think that Earth is flat, I hope nobody here thinks that Earth is flat, but there are people who still think that Earth is flat, then you will just keep going, right? Two parallel lines never meet. But if actually are on the real Earth, even the flat Earth people will discover that they actually suddenly meet with each other. And then they will say, oh my God, there must be, this is destiny. There must be some mysterious force acting between you and me. Maybe it's love or whatever, So, or maybe it's gravity. So actually, so what is happening here is that there is actually no mysterious force acting between them. The two people are just going straight ahead. It's because they're moving in curved space. It looks like their geodesics are meeting and they're meeting each other. And this is the fundamental idea. If you actually also include time in this picture, which is slightly more abstract, but the basic idea, geometric idea is the same. Gravity is basically the gravitational attraction, like sun and earth will come and close to each other, basically because of this mysterious force, which is not even a force. It doesn't exist. It's just that they're going happily along, but because the curvature is, space-time is curved, it looks like two particles are coming close to each other. This requires the notion of relativity of time generalized. So that's why it is called general theory of relativity. And it generalizes Newton's law of gravity and it predicts gravity waves and black holes. Why does it predict gravity waves? Because it was created to solve this problem, which was bothering Newton, of instantaneous action at a distance. So general relativity has it's built into it, this idea that gravity cannot travel faster than the speed of light. And in fact, there is a spectacular verification. Okay, now second one I will say is the black holes now. So why do we now, if you have a universal speed limit, why do we need black holes? So you know that if you throw a ball up, it comes down. If you throw it harder, it goes further and it comes down. If you throw it really hard, like 1 kilometer per second, like a rocket, then it will never come back. And the rocket will escape and go to Mars or whatever. So this is the picture. You know, that's called the escape velocity. So the escape velocity for Earth is about 1 kilometer per second. And once you go more than faster than the escape velocity, then you escape. You are not bound to that by gravity. But now the question becomes, what happens if the Earth, you increase the size of the Earth, mass of the Earth 10 times? Then the escape velocity will go down because the gravitational pull will be more. In fact, if you take the entire mass of the sun and contract it to 3 kilometers, compress it to 3 kilometers, and you're on the surface of this little planet, you will not be able to escape, but even light will not be able to escape. You cannot make any rocket to escape from this planet, and that is a black hole. A black hole is, the force of gravity is so strong that even light cannot escape the speed of the force of gravity. But there is a more refined way, the way physicists understand it. It is called an event horizon, that the black hole is really described by a surface like a sphere, which is actually just a fictitious surface, okay? It's a surface in not a physical surface. So even I could be passing through the event horizon as I speak, or the door of this room could be an event horizon. So the funny thing about the event horizon is it's technically it's called a stationary null surface. What it means is that it's a one-way surface. Like you come into this talk, you find it boring and you want to go away and you want to walk out. You cannot do that. Once you're inside, you're stuck. Okay, so you have to listen to this talk, and eventually you'll be hit with a singularity in your future. Okay, that's, I mean, worse things will happen to you when listening to this talk. So it's a one-way surface. Once you fall inside the black hole, no matter how strong your rockets are and how much efforts you make, you will never escape. So you can fall into it, but you cannot come out of it. Even light cannot escape it. Okay, and this is a beautiful image captured by the LIGO experiment. Two black holes merging. And the little dots are actually stars in the background, which keep moving because the light keeps bending. And they come and collapse and form a bigger black hole. And this was what was observed about a decade ago now by the LIGO experiment. And because the mass of the final black hole is less than the sum of the two masses, using Einstein's E is equal to mc square, all that energy, which is enormously large compared to all the energy that we get from the visible light for that fraction of a second, but it's all in the invisible gravitational waves. And those gravitational waves basically keep traveling. And after 1 billion years later, they were seen in this laser interferometer. So it's actually, again, miraculous. As I said, we are sort of descendants of monkeys and we did this. And so it turns out that these descendants of monkeys had set up this experiment 4 kilometers long, just in time for these waves to be detected. And they detected this in precise agreement with Einstein's predictions. So that is, again, amazing power of the human mind, that the equations that he wrote down 100 years ago actually are completely sufficient and to describe in great detail how the gravitational waves will look. So this now brings us to the final frontier, that you now want to unify this force of gravity with all other forces. And this is what string theorists spend their working hours doing, and also sleepless nights thinking about. Unification has been an inspiring guiding principle. As I said, Salam's electroweak unification was an important milestone for all of us. I remember actually when Salam's Nobel Prize happened, we had just 1979, so we had just entered IIT in 80, So, it was nice, inspiring to see that some Pakistani physicists had made these very important contributions worthy of a Nobel Prize. And actually, in our particle physics course, Mani used to tell us actually how he was also thinking about neutral currents and how Salam got the right ideas, etc. So the 21st century problem is unifying gravity with all other forces. But gravitons, which are the quantum of gravity, just like photon is the quantum of electromagnetic waves, they behave extremely differently compared to photons. And moreover, the characteristic length where these quantum gravitational effects become important is the Planck length, which is like trillion times smaller than the size of a nucleus. So this looks like a very hopeless task. How can you even make any progress? Because we are never going to build a detector. Or, I showed you this gigantic Large Hadron Collider, which barely, and that's where string theory comes into picture. That is actually it's a kind of accidentally discovered theoretical structure, but where gravity is not only possible, but it's really inevitable. I mean, you cannot essentially switch off gravity. It's kind of intrinsically built into the structure of string theory. And the main point is that the electrons, and so these are like two electrons. These lines represent a particle coming in, and they collide, and then they emit a photon, and they create a pair. And, so this is called a Feynman diagram. Gravitons, you can also have a Feynman diagram of gravitons. And these diagrams actually are like a mnemonic. You can, given a diagram, there are rules to calculate what happens, right? How many what is the probability that this electron will go this way or it will go that way, and so on. Graviton, this diagram actually gives you infinity. It's basically nonsensical answer. So what does that mean? That I told you, gravity, sun and earth go around each other, or the earth goes around the sun because of force of gravity. If you now try to calculate this next quantum correction to it, you will find that the force is actually infinite, which is clearly wrong. It cannot be that the force is infinite. So you need to understand how to understand this. And string theory allows you to do that. And the basic idea of string theory is that instead of having point particles, which are going electron and photon, you just have one single string of energy, and it can be oscillating in different notes, like a violin string. It can be either a do or sa re ga ma. So one sa is like a graviton, and re is like a photon. So different notes, musical notes, correspond to different particles. But there is only one single underlying string. So this is very exciting from the point of view of unification, because now you have unified all forces into the excitation of the same string. And this again sounds like a childish idea, no? Instead of points, you consider strings. But it turns out that the mathematics is actually quite beautifully constrained. And instead of now, because everything is made up of strings, you basically think of this point as just a little string, which when you squeeze it, it looks like a point. But it's actually secretly, it's a string. And there is a big difference between this diagram and this diagram. Okay, like this is a graph, what is called mathematically. There are these pointy things where two particles meet, where something hard is going on. Right here, this point is special, right? You can pick this point and say that this point is different from any other point on this line, because this point is where two things meet. And that's where all the problems of quantum field theory come from, why gravity is very difficult to unify with the rest of the forces using this gauge theory principle. See, here it's a smooth manifold. It's a smooth curve. There is no special point. This point, you cannot say, where did this string split into two? You cannot tell. One person will say it split here, another person, depending on how you slice it, you will say different things. So there is no invariant way of telling where did the particle split. And that is actually the fundamental to string theory. This is the main fact why string theory. So roughly speaking, imagine like you had Lego blocks. I give you an analogy of the temple in unification, but this is another. And you have mechanos. And you can build big structures using these Lego blocks, or you can big structures using these mechanos, but you cannot connect the two things. But if you had some screws which connect the two things, then you can build bigger structures. So this is how you unify gravity. So string theory is actually one of the most promising avenues towards unifying gravity. But as I told you, the effects are not seen except at very, very small distances. So how can we even be sure that you are not fooling yourself or you are on the right track? And this is where quantum black holes come in, which is the story of some of my research, and actually where Hawking comes in, who visited VTI in 2001. And he discovered that actually black hole is not black, but it's actually because of this event horizon, it's actually has some temperature. It's called Hawking temperature. And it's like a hot piece of metal. But you know that if something is hot, like this room is hot, you understand it because it's a motion of the quanta in this room. It's a motion of the atoms. So if the atoms are moving in a certain way, this room will be hot. If you now heat it up further, the atoms will move even more faster. And there are many more ways that the atom can go around. So basically, something which has temperature means that there are some bits of which that material is made up of. And depending on the number of ways the bits can organize themselves, you have this notion of what is known as entropy, which is very well known in physics. But if you don't know, it basically tells you how many ways that system can organize itself. Like a jigsaw puzzle. No, jigsaw puzzle you can break it in many ways, but there is only one way in which it is actually all made up together. So different ways of organizing the same system, similar looking system. Like in this room, some atom could be in that corner or in that corner. There are many, many ways in which these atoms can organize themselves. And that's fundamentally the reason why this room has entropy and temperature. And what Hawking discovered was actually quite shocking, that the bits that describe a black hole are stuck at the horizon, which is a surface. It's a bit like saying that all the information in this room is encoded on the walls of this room. Like you sort of divide these walls in some small units, the Planck length, and then in those units you have ones and zeros. It's like ones and zeros written on the wall. And that contains all the information about whether the chair is here, the table is here. Now, that sounds a bit weird because you would think that you need information which is the bits at every point in the volume, in the entire room, that, okay, here in this, there is 1, and here this is 0. Here there is wood, there is no wood, right? You need information at every point in the volume, but instead of that, it's at every point on the surface. And so it's really very unlike normal matter. And then the question becomes, suppose I give you a black hole. Can you count how many qubits? So this is like a qubit, quantum bits. How many qubits does a black hole have? And that question actually turns out to have a very dramatic answer, and we sort of come full circle. And this is what I would call unification of ideas. That what people discovered, I showed the photo of Juan Malsena before, that the horizon of a black hole actually is a hologram. It's like a hologram, a film. Like a hologram is a film which contains three-dimensional information. And it is described by this gauge theory that I told you before, SUN gauge theory. So for some, I'm simplifying a little bit, but the basic idea is this hologram, which contains all the information about the gravitational physics of the black hole, is described by this very non-gravitational theory, which we talked about, for the describing strong nuclear force, okay, or weak nuclear force. This is shocking, because imagine there is a theory in which things fall, right? There is gravity. It's supposed to be exactly equivalent to a theory in which nothing falls at some quantum level. And it almost sounds like madness. And I think we are still trying to understand what does it mean. And I think there are lots of very concrete mathematical calculations and tests which show that this actually is true, but the full implications are not yet fully understood. So now we have really come full circle. We started with gauge theories describing all the forces of nature except gravity. We started with gravity and we had black holes, and then Hawking discovered that it has these qubits, and those qubits are described in terms of gauge theory. So, and we invented string theory to solve these problems of divergences, infinities. So somehow the ideas are also connected, not only. And here is where I will show you this. One of the problems of counting these, how many qubits are there, turns out to be related to some very nice mathematics of Ramanujan. So Ramanujan had this famous, and this is a question that I can pose anybody, even school children, that how many ways, suppose I give you an integer like 3, how many ways can you partition that integer into like 1 plus 1? So if you had just had one color, you can do it as 1 plus 1 plus 1, 1 plus 2, and 3, right? Only 3 ways. Suppose you have 2 colors, then you can do it in 10 different ways. If you have more colors, 24 colors, then you can do in more different ways, right? And Ramanujan found a very beautiful formula to calculate this number. And now this is where I will show you this movie. This is from The Man Who Knew Infinity. Ramanujan is here, and this is Hardy, who was his mentor and who, of course, a collaborator, who had enormous respect for Ramanujan. I mean, he put Ramanujan, I mean, he realized that Ramanujan is like a once-in-a-century kind of a genius. And he's taking him to meet Major McMahon, who was one of the famous combinatorians, whatever you call it, famous mathematician working in combinatorics, who was kind of racist, as you can see from the, okay? So here is...
Enter at your own risk.
Enter at your own risk.
Ah, I've been waiting for you. Square root of 58,639. Now.
242.
242 what?
Oops.
Same number squared.
3,438,532,321. Ah! Thrashed you! Combinatorics, that's what I do. Glorified dice throwing. Bloody nerve of you both. You fail on primes, and you think you can just turn round and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
No, I will. By hand. By slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can do it.
Okay, so I will read, because the sound was not good, but basically he says, I told you, P of 3 we calculated, no? You can calculate 1 plus 1 plus 1, 1 plus 2, 3. There are only 3 ways. If you have more colors, you can do it in more ways. He's saying, can you calculate P of 200? Now, it's not so easy. Try doing it. You will work for days, because you can do 1 plus 1 plus 1, 1 plus 2, 199 plus 1, 198 plus 1 plus 1. It actually grows exponentially, okay? So you cannot actually do it, and you need some sophisticated combinatorics methods. But Ramanujan had an analytic method. So this is called analytic number theory. And he wrote a beautiful formula. This is actually called Hardy-Ramanujan-Rademacher formula. Exact formula for the people in the, so it's given in terms of some Bessel function, some phases, number theoretic phases. But, you know, this Bessel function is like a function, you know, sine and cosine. You can put it on a computer and just, suppose you want to calculate P of 200, you just, this is with 24 colors. You just put 200 here, and you get the answer in no time. Whereas McMahon would do it in his laborious way. So he says that, okay, he challenges him to calculate P of 200, and he says, okay, then you crawl back to whatever rock you came from, India, etc., etc. So this is the, when there's go down.
Well, here we are, P of 200, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
So some very similar formulas actually turn out to be important in the calculations. This showed you this exact formula. And what is beautiful about that formula in the context of string theory is that you can actually calculate it in two different ways. So this is what we did in our work. You can calculate this infinite series, one term by one term, using some methods in path integral localization. And you can calculate this integer from some other methods using gauge theory. So gauge theory is equal to string theory is now spectacularly you can verify in this particular simple context. It is an idealized black hole, not a real black hole that we saw. It's a supersymmetric, etc. But it's a kind of a very powerful confirmation of at least the logical consistency of the theory. Precise agreement with Hardy-Ramanujan, and somehow gravity knows about some integer. It's like a gravity, that information about that integer is sort of pasted on the horizon of a black hole, on this hologram. So this now really is the idea of unification of all forces. The quest for the unification of gravity and other forces continues. There are fascinating connections between quantum black holes, gauge theory and string theory, now also quantum entanglement and the structure of space-time. This is also becoming an interesting topic of research. And I would like to now end this part of this, and then I have a few minutes to go back to the previous theme, Einstein's encouragement and warning. So those of us who are engaged in this must keep this in mind. It's both an encouragement and also a warning. Because we don't have direct experiments, because of the historical times we are in physics, where theory is really reigning supreme. A theory is so good that we don't need, apart from these kinds of logical inconsistencies, we don't really need anything other than our theories that we have. General relativity, they work fine. You don't need to do anything more. But if you are really bothered, like Einstein was, by this logical inconsistency between these two theories, then you are really led. So he says that successful attempt to derive delicate laws of nature along a purely mental path by following a belief in the formal unity of the structure of reality encourages continuation in this speculative direction, the dangers of which everyone who dares to follow it must vividly keep in mind. And the dangers are indeed that you can be led astray after 10, 20 years of work. And this is something that one has to keep in mind. But this also underscores the unity of science. You know, Ramanujan, Hawking, Einstein, coming from totally different parts of historically different times, and all these very different concepts. So this tells you that you cannot actually separate science in blocks that one is intended to know. So now let me come back to the, finally in the last 5 minutes, the theme of uniting the world and what does ICTP imagine for the next 60 years? So the first question is that should we be even doing curiosity-driven science in a place like TIFR or in a place like ICTP when there are bigger problems in the world we have to address, you know, maybe primary education. But I think it's, you know, all these other considerations are also important, but curiosity-driven science motivates excellence and it attracts talent because young minds are excited by amazing things that we heard about and they want to learn more about it. And you don't want to tell them, no, 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 don't do this. Don't satisfy your curiosity, do something else. It crosses interdisciplinary boundaries very easily. I mean, it's relatively easy for theorists to start doing something else, jump onto something else, much more so than for an experimentalist. Or in maybe a technology mission-driven thing where they really have some particular mission that if you're building rockets, suddenly you cannot start building supercomputers, you know. So making truly disruptive technologies also can come out of this curiosity-driven science. Latest example is like John Hopfield, who was a statistical condensed matter physicist, and this neural networks architecture that he invented it, you know, playing with the statistical models, and that became the basis of the neural AI revolution. And of course, I'm not suggesting that we should emphasize, you need a healthy balance between pure and applied science and a healthy balance between theory and experiment. But the advantage is that theory is cheap, you know, it doesn't require hundreds of millions of dollars. So fundamental science is the driver of technology. It's very important to appreciate this essential unity because without quantum mechanics, you cannot have quantum technologies, or without basic physics, you cannot have artificial intelligence. An overemphasis on technology is short-sighted. This is the slide, okay, not necessary here, but I use it when I'm going to Delhi or to Rome. And there is a nice quote of Euclid. When Euclid was asked by Emperor Ptolemy to teach him geometry, Euclid tried to teach him, but Ptolemy found it very difficult. So Ptolemy said, "Can you simplify it for me?" And Euclid has told him that there is no royal shortcut to geometry. So there is no royal shortcut to technology. Okay? Because otherwise we will be just consuming the technology and not creating it, as we said before. So the next Ramanujan, Ramanujan was a chance discovery. Ramanujan could have been lost, actually. This amazing genius who really is keeping mathematicians busy even today, his work would have gone completely unnoticed and completely lost if he did not have the fortune of meeting Hardy. So how to create conditions to nurture the next Ramanujan? And there are two visions, okay, speaking, and this is what I was telling Sandeep, that I have been fortunate to see both these visions at close quarters. There is a vision of Bhabha, but also, of course, Meghnad Saha and others that I'm not mentioning here, but I'm seeing some at Tata Institute, to create strong scientific communities in India. And that, of course, is our final goal. Salam's vision is to create an international hub for science. And when I became the director, I had to sort of do some soul searching about what should be the mission of ICTP. Is ICTP even relevant in the future? Should we not? But I came to the conclusion that actually I think Bhabha and Salam were not exactly friends. I think they somehow, it always happens because everybody has their own vision and they pursue it and they don't necessarily talk to each other. But I really think that these two visions are complementary, should be regarded as being complementary and not contradictory with each other. Because internationalism of Indian science, even while we are creating strong communities, remains very important. We need a global platform for some of the global challenges. In particular, things like cyclones and pandemics, they don't respect. As far as monsoon is concerned, Himalayas are just a boundary condition to Navier-Stokes equation, right? It's not a geographic political boundary. So any viable climate action, if you exclude climate scientists from the global south or from India or from Bangladesh, it clearly cannot be right when it comes to negotiating at the negotiating table. So it's very fundamental that we have equal partnerships with global south. So ICTP actually has, I just signed this agreement with the Ministry of Earth Sciences to hold climate workshops at ICTP where scientists from Bangladesh and from Pakistan, China, India can come together to share scientific information. So this actually is going to be fundamental importance, this role of ICTP, given its unique mandate as an UN organization, whether it is AI, quantum technology, I mean, apart from the core areas like particle physics, even in these areas is going to be very important. So with this in mind, I have also, this is one of the strategic priority we have identified, because now, as we said, AI has become so powerful that it has really emerged as a third pillar of science. We used to think of theory and experiment, but the 2023 Nobel Prize was given in quantum chemistry, sorry, last year maybe, I forget. The AlphaFold for the protein folding problem was a very difficult problem of many years. The scientists really didn't know how the protein actually folds given a DNA sequence. And it is solved not by theorists, not by experimentalists. It was solved by an AI, Google's AlphaFold. That's what got the Nobel Prize. So I regard it as an obligation of ICTP, an institution like ICTP, to find the means to make these critical resources globally available. And this is what I have called an International Science Alliance, because now countries like India, Brazil, and China are no longer, the BRIC countries are not developing countries in the old sense. So it should be an equal partnership because there are strong communities existing here. There are financial resources. So, and there are areas where we should really collaborate as equal partners. And with this idea, ICTP has been successful in the last few years, 4 or 5 years, to have agreements with universities, corporations like IBM and Quantinuum, supercomputing facilities in Italy and Switzerland, foundations like Simons Foundation, Arab Fund, or also countries like South Africa, Brazil, Kuwait, hopefully now with India, and maybe in future China. So I will end here. So I like this kind of symbolism for ICTP as a lighthouse for global science. This is the Faro della Vittoria. It's a lighthouse in Trieste. And you can see ICTP is in the background over there. So I envision the ICTP of the next 60 years, not only as a place for developing countries, but as a lighthouse for global science. Thank you.
Thank you very much, Atish, for that talk, spanning so many different ideas and threads of thought. Floor is open for questions. I don't see. Okay, here's one. Go ahead.
So you told us about the entropy of a black hole. Is it a theoretical thing, or can you actually measure the entropy of a black hole?
Yeah, so again, that's an example of, so Hawking's calculations, every serious physicist believes in it, because it is based on really well-tested fundamental principles like quantum mechanics, general relativity, which we understand very well, and thermodynamics. So, but there is no possibility in near future that you will actually measure Hawking temperature, because the temperature of a black hole is inversely proportional to the mass of the black hole. So for a black hole that we see in the real world, the temperature is so low, it is lower than the cosmic microwave background radiation. So the black hole is, so the question, so this kind of question is really valid, that how can we even be sure? But there are, so I mean, that's why Einstein's warning is also important, that, you know, we have to tread carefully. But there are wonderful examples. If you look at the history of physics, let's say in the 19th century, some of the far-seeing physicists of the time, like Maxwell and Gibbs, for example, you must have heard about the Gibbs phenomena. He discovered that there is an n factorial missing when you do the counting. And he just inserted it by hand, by this argument that thermodynamics must be extensive, okay? And he put it by hand. It took actually, I don't know, 70 years, because to really understand that n factorial requires the spin statistics theorem, which comes in quantum field theory. You cannot derive it from first principles. Or Maxwell understood that, I think it was Maxwell, that if you take a diatomic molecule, I mean, the specific heat actually of diatomic molecule comes out wrong, again because of the quantization. And he was really bothered by that. So he said that there is something fundamentally wrong with classical statistical mechanics. So statistical mechanics sometimes can be a good way to probe, and Hawking's results are sort of combining thermodynamics with quantum mechanics and general relativity, because of which I think it's a reasonably reliable guide, so that you don't really go off rail. But nevertheless, it's not an explicit experimental verification.
Just to say that that's of course true, but luckily the answer for the entropy turns out to be very geometric, as in the area which can at least be now measured with the Event Horizon Telescope and other means. So
I mean, some things like, for example, the entropy is proportional to area, what he's referring to. So the fact that if it is, some of these facts you can verify, because if it really is the entropy is proportional to area, then it should always increase, right, in any physical process. So there is actually classical theorems in classical general relativity that area always increases. And this you can verify, that when the two black holes merge, can you have an event when the final area is bigger? And that will never happen, because it is forbidden by the second law of thermodynamics.
Great. Anyone else? Yes, Prabhu out there.
Okay, very nice talk. I came a little late. So my question is about what are your comments about the dark matter, and whether string theory is able to say anything about the existence of dark matter,
The dark
or
sector.
those kinds of.
I mean, dark matter can be incorporated in string theory. That's not difficult. But dark energy is more complicated. These are really two of the biggest mysteries in modern physics. And as of now, string theory doesn't have any particularly useful angle other than, but I mean, basically there are lots of ideas for dark matter in particle physics, or even non-particle physics, I mean, brown dwarfs, black holes, I don't know. It's a really kind of, there is no thing with which you can grab the problem. I mean, basically you have to explore many, many possibilities, all the possibilities. And which one of them I mean, the data is, the information you have is very little. You only know from gravitational phenomena that it exists, but you don't have any other direct information.
Any other questions, comments? Okay, well, let's thank Atish for a great job.